When we look at the 1980s, this is the period when quantum progressing started properly. Around the 1980s, when the history of quantum computing began and was fully formalized. In prehistory, when humans started to think of computers and information progressing as physics and got better, you would simply need to use all laws of physics to derive what ultimately makes in our universe on computer. During this, our laws of physics to derive quantum physics must be used to derive computation and universal rules or laws of computation. The first step came with a quantum mechanical model of computation, and our computation was modeled this Turing machine. In 1985, we were introduced to more abstract concept, the universal quantum computer, and began to be used a new computational model of quantum Turing machine. In 1992, this algorithm was designed to solve a problem that the algorithm would solve instantly. Thus, a run of the algorithm would solve the problem quantum algorithm. But its robustness was questionable. It was replaced due to noise or a different problem, and the acceleration was started. By 1994, the classical algorithm was exponentially faster and less time consuming. The first foldable exponential velocity appeared, taking advantage of algorithm, Scholl algorithm. Namely, factoring is a problem that attracts a lot of people, including cryptographs. In order to solve problems, quantum computing starting in 1994. It was 1995 when quantum error correction was introduced. This device seemed to some kind of continuous computational model. This is why quantum mechanical systems have continuity as opposite bits that are discrete. So error correction, copying, and saving became easier. For example, if you tried to record a mixtape using the radio, an old cassette type, the quality decreased when analog music is copied. But of course, you can copy as many CDs you want without any loss in quality. So the suggestion is quantum mechanical model computation, which is very similar to analog computational models. In 1995, it was really an indication that error correction could be made using a quantum error correction. But mistakes would pile up, and there were other techniques that could be applied to make mistake tolerance. In 1997, if the process causing noise and errors was below a threshold, the quantum computing became possible indefinitely. In fact, it showed that we can do any quantum computation, that is everything that quantum physics allows, with a very small number of gates. We can now perform quantum computation in fault-tolerant and efficient manner.
I will inform you about the quantum computers, how does it work, and their difference than the normal computers. To understand its properties, let's check the normal computers that we are using in every part of our lives. Normal computers works in a binary system. A single bit can be either 1 or 0, but the quantum computers work completely different, actually. So the quantum physics describes the behavior of atoms and fundamental particles, like, for example, electron and photons. So the quantum computer operates by controlling the behavior of these particles. Their bit is completely different from the normal computer's bit. Let's call it a quantum bit. Quantum bit has more, a fluid, complex, non-binary identity. It can exist in a superposition or a combination of 0 and 1, actually, with some probability of being 0 and some probability of being 1. For example, it could have 75% chance of being 0 and 25% chance of being 1. It can be 90 to 10, 65 to 35. The possibilities are endless. The key idea is that we have to give up on some precise values like 0 and 1, and we should allow for some uncertainty actually. And I want to give an example about the game. A game played with both normal computers and quantum computers. That game project belongs to Dr. Shoshini Ghosh, and she's a quantum physicist at Wilfrid Laurier University. As you can see, the game is very simple actually. The first, there's a coin with heads. The first turn is computers, and it can either flip the coin or not. Then we play it. Also, we can flip the coin or leave it as it was. The final move is computers, and it can also do the same thing. After that, the coin reveals. If it had, computer wins, and if it tails, we win. Actually, yes, it sounds like a simple game, and the probability of winning should be close to 50%. Also, Dr. Shoni let her students play with the normal computers in this game, and their win rate was like this. It's really close to 50%, as you can see. But if we play this game on a quantum computer, what happened? Any guesses on the win rate? So she also made this with participants with 372 people. And yes, as you can see, the win rate is nearly impossible. She also claims that the 3% that we have is because of the computational error. So let me explain. So during the game, the quantum computer creates this fluid combination, as I told previous slides, of the fluid combination of heads and tails, actually, 0 and 1. So that no matter what the player does in our turn, if we flip it or no flip, doesn't matter. The superposition remains intact. In final move, the quantum computer can unmix the 0 and 1 and perfectly recovering heads every time. So because of that, we lose every time. There is no actually win chance in this game for us in our daily lives.
I will briefly talk about the usage areas of quantum technologies, and then I will talk about our main topic, which is quantum computing usage areas. Firstly, I want to mention about quantum sensors. It can measure physical quantities such as frequency, electric magnetic field, and temperature very precisely. In addition, quantum sensors can be used in different fields, from satellites to airplanes with different applications. Quantum computers, unlike classical computers, operate with qubits and store data. For this reason, it performs calculations even faster than supercomputers. Therefore, in the fields of aviation and medicine, where fast computers are needed, many problems will be solved very quickly. Now I will mention about quantum secure communication. When it was realized that quantum computers could easily break existing cryptographic systems and a serious security vulnerability would occur, studies in this area also start. In this direction, work continues on quantum secure communication mechanisms such as algorithms, switching systems, and authentication. Lastly, quantum simulation. While it is not possible to model complex quantum systems with supercomputers, quantum simulators allow. Now, I want to mention about quantum computing usage areas. It helps daily life a lot. Now, I will give examples about that. Firstly, improving weather and climate change forecast. Because quantum computers can analyze all the data at once, meteorologists will have a better idea of when bad weather will hit people to save lives, avoid suffering, and loss of money. The United Kingdom Met Office has already invested in quantum computing technology to help improve forecasts. We can learn more about how we affect climate because quantum computers will help us build better climate models. That part is important, especially who lives in Istanbul, I think. I want to talk about traffic control. Whether in the air or on the ground, quantum computers will help facilitate traffic control. Optimum routes will be quickly calculated, allowing efficient scheduling and reducing traffic congestion. Now I will talk about quantum algorithms for learning, which is artificial intelligence. Development of quantum algorithms for quantum generalizations of classical learning models. It can provide possible speed-ups or other improvements in the deep learning training process. The contribution of quantum computing to classical machine learning can be achieved by quickly presenting the optimal solution set of the weights of artificial neural networks. Lastly, quantum search. Most search algorithms are designed for classical computing. Classical computing outperforms humans in search problems. On the other hand, Love Grover provides his Grover algorithm and state that quantum computers can solve this problem even faster than classical computing. Artificial intelligence powered by quantum computing can be promising for near-term applications such as encryption. Thank you for listening to me. Now, Melisa Atalan will speak.
So let's talk about the application of quantum computing in the field of chemistry, health, and environmental. Firstly, let's look at healthcare and life sciences. The application of quantum computing to healthcare and life services is poised to revolutionize the treatment of diseases. Such a revolution is likely to increase the pace and precision of disease identification or drug discovery or genomic analysis. Another potential use case for quantum computing is precision medicine, like the design of individualized interventions and treatments. So existing treatments protocols don't take into account individual genetic and biological factors or environmental factors that can boost the treatment's impact. For example, consider that 31% of patients can safely metabolize tamoxifen, which is a common cancer treatment, or that there are more than 7,000 known rare diseases affecting more than 30 million people in United States alone. And that's it's the most, so the most of them are incurable or have very expensive treatments. By helping shed light on the correlations and dependencies of various contributing factors, quantum-enhanced machine learning could advance medical research. With it, researchers could predict the effect of drugs and treatments, design individual treatment plans for them that could improve more patients' outcomes, and even forecast the risk of future diseases to allow for earlier or preventative treatment. Secondly, material science and discovery can be identified as another subtopic. Material designers use complex calculations to predict the mechanical, optical, or physical properties of ceramic, glasses, polymers, and also composite material. Quantum computers could help design engineers to create better materials by giving them more precise control over molecular reactions. To create the most efficient solar cells, and the energy resources seek to understand the interaction of sunlight with thousands of combinations of silicon and polymer-based material. More accurate predictions of how materials interact with light could help them to create more efficient solar panels and LED devices. Likewise, energy companies are working to test, develop, and scale carbon capture technologies that use less energy to strip carbon dioxide from power plant emission. Current carbon capture methods, which rely on water to absorb carbon dioxide, are costly, inefficient, and polluting. And scientists have recently developed absorbent solids that can be used for more effective carbon capture. Quantum computing could help build on these innovations, leading to discovery of highly absorbent solid materials for capturing carbon dioxide. So let me give another example for chemical process simulations and optimization. Quantum computing could also help scientists to develop and test new industrial processes that could help to conserve natural resources, reduce emissions, or lower the cost, and also for speed production. For example, large scale of production of ammonia-based fertilizers relies on the Haber-Bosch process, which is a 100 years old and energy-intensive method of nitrogen fixation that consumes between 2 and 5% of world's annual natural gas production. Producing fertilizers using the Haber-Bosch process alone accounts for 1 to 2% of world's annual energy supply and is responsible for also 2 to 3 of global carbon dioxide emissions. Similarly, the production of hydrogen for use in hydrogen fuel cells relies on industrial method for splitting water molecules into hydrogen and oxygen. But these existing methods are also very energy intensive and rely on expensive and rare material and creates waste carbon, which limits the use of hydrogen as a clean green source of energy. Quantum computing could streamline both processes by enabling scientists to discover new catalyst materials that would reduce energy requirements for ammonia production or water splitting. This would result in technological breakout for producing fertilizers and hydrogen fuel cells. You can see our references.